Good morning. So now today's topic, and today's topic is, say in general, what I wrote is transport across body compartments. So today's topic, as such, it is divided into two parts, and both are very logical. So we'll start with the basics, and then gradually we'll see that how can we really measure the various body compartments, that is how much fluid it is there, and what really happens if you give a normal saline, what happens if you are running a marathon, what happens when there is some problem into the say specific hormones. All those things we'll see from the clinical aspect also. Now every time I'll be asking you the questions that, okay, this is the situation, tell me what would happen, right? So first I'll explain the entire basics, and on those basics only we'll be coming across 6 scenarios, right? It is like 6 scenarios. These 6 scenarios will cover every condition of the body. It is like, once you know this, in clinics you have to just understand that in the body, is there increase or decrease in the fluid, and if the fluid is increased, so then what type of osmolarity is there, right? So we'll talk about it. That will give you tremendous cutting edge over when you'll be into medicine. Okay. Few emails they were there. One of the email was it's like, well, you are a third year student and you have asked that how should I really start now, because there is, what is to increase hemoglobin fast in it. Okay, tomorrow we'll take this question, how to increase hemoglobin, etc. Right? Because tomorrow is Saturday, so Saturday is it's like a free day. You can ask any question. So right now we'll deviate, totally deviate from the topic there. So that's why I'm not taking. I don't have any problem, but we'll deviate from the topic. Regarding, I'll just pick up 2 3 emails. One email was that you are in third MBBS and still there is problem in physiology, etc. Well, gentlemen, ideally it should not be like that, but doesn't matter, right? This is the physiology which we'll be taking in reasonable depth. Now there are few videos already which I have posted over here, right? They are already there. Last year I prepared that. So when we'll be reaching to those topics, I would insist that, say, better you watch those videos so that we can proceed further with the newer topics. Right? My intention is to put the way almost the entire anatomy is put over here, right? Except the thorax, which I'll be starting from Monday. So that will put entire thorax, the entire body, all regions over here onto our channel. Similarly, I wish to put the entire physiology, right? And in such a way so that you don't have to cram. Few emails regarding, say, that should I do the job, etc. So for that I would insist that please watch yesterday's video, the initial part, right? That 20 minutes will answer most of the questions. Okay, so now let's start with our today's topic, because today's topic is also, yeah, eat cheeky. So today's topic is, we start with cellular fluids. Cellular fluids, very basic topic, or the body fluids, right? This is like also known as the body fluids. First 5 minute will is like known to everyone, right? But why I'm taking it, as it was a request which was made in few of the emails that please up sir thoda background le lijiye and then you come to the topic, no problem, right? That can be done. So in the body fluid we say that it is the water which is most important, correct? As such, the water in the body weight, almost 60% is the water. 60%. So if my weight is 80 kilogram, so that means 8 6 are 48. So 48 kilogram is water, right? Now this water, 46 kilogram is water. Now this water is divided into two parts, right? The fluid, intracellular fluid and the extracellular fluid. As this topic has already been taken, so I'll be going bit fast. right? Intracellular fluid means it is the fluid which is inside the cell, correct? Inside the cell. Extracellular fluid which is outside the cell. Outside the cell, this is inside the cell. Inside the cell. Outside the cell, that means it has got two areas. One which is between the cells, so we'll call that interstitial fluid, right? Interstitial fluid which is between the cells. Arey baap re. These spammers, so they are put this hide user on this channel. So interstitial fluid which is between the cells, right? Between the cells. And plus other is into the blood, that is the plasma, right? Plasma, which is into the blood. Okay. So ICF, intracellular fluid, which is comprising of about, say if we say 60% water, 60% of what? 60% of body weight. ठीक है? 60% of body weight. Out of this 60%, 40%, right? So that is about 2/3, right? 2/3, that is 40%, is inside the cells. So with our calculation, if we go for it another, so it would be about, it would be what? 40, so 40, 8 4 are 32, so 32 kilogram. 32 kilogram water is inside the cells, correct? And rest 1/3, that is the ECF, extracellular fluid, which is outside, and that would be 8 3s are, and this would be 20%, right? It would be 20%. So 8 2s are 16. So it is like 16 kilogram of water, right? That comprises of interstitial plus plasma, both total. Perfect. Another concept, changing the color. There would be cations. These words will appear again and again and again at so many places, right? In order to avoid confusion, we use positive ions and negative ions. But in book, yes, there would be mentioned like cations and anions. No confusion. Anion, I used to confuse between consa positive, consa negative, honestly, right? So then I remembered it like this, that anion is a negative ion. So someone must have given the name like this only. So now there is no confusion. Anion means they are negative, a negative ion. So obviously cation automatically becomes positive. If we talk about intracellular fluid, so in intracellular fluid, cations, that means positive, right? They are, say, potassium, magnesium. We won't be discussing that sodium potassium pump etc today, right? That will take next week. Is superb, it's rocking all such concepts, right? But today's concepts, they will be helpful at all levels. And negative, say some proteins, right? Big proteins, they are negative, right? Then phosphates, organic phosphates, right? So they are negative. So that is anion and cation. The concept is that whatever the number of anions are there, make a total of it, and whatever the number of cations are there, make a total of it. They both should be equally equal, right? That is what is called as the macroscopic. This is just a name, but the principle is very simple. Everything should be electrically neutral, right? So this is the principle of what is called as the macroscopic electroneutrality. Electroneutrality. Neutrality. So these are like some words where you want to impress someone, so then you can do that. But basically it tells that number of positive ions should be equal to number of negative ions. Bus, that's the meaning, right? Even I was happy with this negative ion. So I was so happy. And then, Deepak, what happens once you remember this, na? So then even in your viva, or you want to explain something, deliberately you use, instead of negative, you say, acha, these are the anions which will be crossing the membrane, and you know that how have you remembered, but say it makes an impact. Okay. So macroscopic electroneutrality. This also word is like that just to impress, right? When you say, if you say that positive ions and negative ions are equal, those people say, हाँ ठीक है. Right? When you say, okay, there is macroscopic electroneutrality into the intracellular fluid because of the transfer of potassium, people say, wow, kya wow, right? It means almost the same. Electroneutrality in cell, right? Or on membrane. Aishwarya, it is in cell, right? It is in cell because membrane is so, as such, negatively charged, right? We'll see that thing when we'll be talking about action potential. But right now we are talking about inside the cell, intracellular. Same thing would happen even in ECF also, but we'll come to that because there is slight change. But so far good. So I'll agree to that. In the cell, right? Right. Right. In the cell. Right. No confusion. Great. In cytoplasm. Perfect. Perfect. That is more appropriate. Yeah, Z line. You have remembered it. Vish and Shive. Now comes new page for the measurement. See, all these things, they look so, sometimes don't you think they look hypothetical? कि यार सही में ऐसा होता होगा अंदर, right? Things look very hypothetical. Let's calculate it, right? Can we really measure it? Let's see how to do it. See, this is just a beaker, right? And in this beaker, there is some water. Put some water, right? So you can measure the amount of water, right? But think it like, it is okay, you can measure, but what if this amount is unknown amount and there are no markings on this beaker and you just cannot take the entire water out, right? So this is like, because you cannot tell a human body, let कि चल तेरा पूरा fluid खाली करते हैं, measure करके वापस भर देंगे. It cannot be done. So this is like body, there is a fluid inside, but there is unknown amount of volume. We don't know. So that's why let's call this as Vx, right? Vx, which we don't know. Now to measure this volume, what we have to do, let's add something into it, right? Let's add sugar into it. 1 चम्मच sugar, right? We add into it and it gets, say, suppose mixed, right? So that will, because we'll be able to measure how much sugar concentration is, so this will be used as an indicator. So indicator, when it is added, right, when the indicator is added, we can even think like we add color, right, anything which can be measured. So when we add, obviously this indicator will be diluted, correct, right? Indicator is diluted, so diluted indicator. Now this indicator will assume a particular concentration. What I mean to say is, right, very crudely I'm telling, say if the fluid inside is 5 liters, or let's keep it even more simple, if this fluid is 1 liter, and to that you have added an indicator which is, say, 10 ml. So 10 ml is known to you, and you don't know that how much is this fluid, because this is unknown, right? This is our Vx. But this 10 ml will get mixed into 1 liter. right? So because it is very small, so let's consider that it becomes say 1 liter and 10 ml. But now you take a small sample out of it and measure that how much is our indicator, correct? So that is how you can really calculate. Okay, if there is a 1,000 part, if there is a 1,000 part of this indicator, so that means whatever the fluid which you have taken out, multiplied by 1,000 and you'll get the actual fluid. So the meaning is that diluted indicator, and this indicator assumes, right, it gets a particular concentration. This is called as concentration, right? In this much water, how much it has got concentrated. So that's the formula. That is the amount. Total amount is how much? Amount is concentration, right? What is the concentration into volume, right? Into volume. So that will give us a clear indication. We'll take a practical of it. Right? Now over here, we want to measure the volume. The amount which we have taken out, we know that. How much we have injected, we know that. How much we have put the indicator is known that. We have measured the concentration, that is also known. So in order to measure the total volume, all we have to do it, you have to just reshuffle the formula. Volume is equal to amount upon concentration. Amount upon concentration. Let's pick up a real good practical, right? And this thing will explain things in very easy way. Technically speaking, this is called as the dilution method, right? It is called as the dilution method, right? Because we are actually diluting our indicator. There are few principles. Sometimes you have to remember some principles. So this principle, it has got a name, and that name is called as Stewart-Hamilton principle, right? It is called as the Stewart-Hamilton principle. Well, in exams, sometimes it is asked, so worth remembering. I would say that you do remember. Okay. From this point onwards, we'll draw one figure only till the end for all our understanding of ECF, interstitial fluid, and the intracellular fluid. Okay? So like this, we'll draw like this, we'll draw like this, and we'll draw like this. So this is our intracellular fluid. This is our interstitial fluid, correct? And this one is like our, say, plasma. So truly speaking, this is our ECF. This is our ECF, and that's our ICF. Because ECF is combination of interstitial fluid plus plasma. All good? The total of ECF plus ICF is total body water. Okay, na? Right? When we were telling the total body water, which is 60%, right? Which is 60%, and out of which ICF 40, ECF 20, and that's the total of it. So it is ECF plus ICF. Right? So this is 40, this is 20%, this is 20%, so total is 60%. That's how things go. Now there is a small table which I am giving you, and yes, you have to remember it. It would be very useful. But apart from its use, interesting is that you have to actually visualize that yes, what it is doing, right? So first thing first, same figure, right? But now we will avoid writing, right? And I just do this and do this. So now you know, right? So this is intracellular fluid, right? ICF, and rest is ECF. and we shall inject the things from here. So you consider that this is our blood, right? This is the blood. In bloodstream we are adding. ठीक? Oh, body content water is 70%. Yeah, it is. That's what we'll be discussing soon. It varies from person to person. In female, it is less, right? Because water, it is directly proportional to fat, and in females, because of the body constitution, the amount of fat is slightly higher, relatively higher, right? So that's why there would be less water. So if someone is very strong, if the muscles are more, so they'll be carrying more water, they'll be having more water, right? Because muscles are more, so fat would be less. Acha. Chalo. So this is the figure which will, when I draw like this, it means we are injecting. Injecting where? Injecting into the bloodstream. Okay, we are injecting into the bloodstream. When we are injecting into the bloodstream, we are injecting into ECF, extracellular fluid. Comes the first part. We want to measure total body water. Total body water, right? By the principle, we have to inject something into the tissue, into the bloodstream, so that it goes everywhere. We want to check whole body water. That means it should go into the ECF. At the same time, it should pass through and it should go into the ICF also. It means it should pass through the cell membrane, right? Because you are injecting into the blood. Such substance is like deuterium or the heavy water, which is called as D2O. It is called as the heavy water, or the tritium, right? These are all very special substances. This is heavy water, right? Heavy water. So what they will do, they will go everywhere, right? They will literally enter into ECF, interstitial fluid, even the intracellular fluid. So when you measure this concentration, you will know the total body water. Fine. The next one. If you want to measure only extracellular fluid, right? Extracellular fluid. Yes, hydrogen isotopes, exactly. If you want to measure extracellular fluid, what you have to do? You have to inject such substance which should not be able to pass through the cell membrane, right? When you are injecting it into the plasma, it should be able to go to the interstitial fluid, but when it will come to, say, this intracellular, at that point it should be stopped. Okay, no, you are not allowed to enter into the cell, right? It won't be allowed into the cell. Perfect. So that will give us the entire indication of how much this area is. Full area minus intracellular fluid, right? So neat. Such substance are, it is, and I am cutting this S so that you never make mistake. It is not insulin, it is called as inulin. This is the most common, right? It is INULIN. Inulin. This is most common. So when the inulin is injected, right? When the inulin, it would remain into extracellular fluid. That means it will go into the interstitial fluid and in the plasma, but not in the intracellular fluid. Crystal clear, right? Rest all are very standard, like say mannitol, right? It is also used, right? Mannitol or sucrose, right? Sucrose, or say sodium thiosulfate, all these are having the same property. But the idea is they won't enter into the intracellular fluid, right? Because they can't cross cell membrane, right? Cell membrane. Makes sense? Correct? Okay. Now, if you are, say, very enthusiastic, you see, I want to check the plasma volume, right? that out of this, I am not interested in this interstitial fluid. I just want that how much is the plasma volume, right? Plasma volume, something which is present only in blood. So that means you have to inject something which will go and attach to the albumin. Albumin is into the plasma, right? So when it will attach to the albumin, you'll be able to judge that how much is the plasma. So that is best is that albumin is a protein and you can, it is called as the radio labeled albumin, right? This is one of the very powerful system, right? Or there is one dye also, it is called as the Evans blue, right? It is called as the Evans blue dye, right? This dye also attaches to the albumin, and that's how you can make a judgment. You must have noticed one thing: there is no substance which can measure, right? Inulin enter or not. Inulin means where it enters. Inulin means entering into cell. No, it cannot. Inulin, mannitol, sucrose, sodium thiosulfate, none of them can cross. They can't cross cell membrane, right? They can't cross cell membrane, because if they cross cell membrane, so in that case, so they will be measuring not ECF, but they'll be measuring the total body, right? I didn't understand total body water point. D2 is harmful, right? As it shows. See, there are some substances, if given in large dose, it can be harmful. But small doses, not a problem. As such, the radiation is also harmful. But in small doses, it's okay. No, there is no direct. Exactly, Siddhant. I was about to say that there is no method by which you can measure the ICF. There is no method by which you can measure ICF directly. ICF cannot be measured directly, right? It cannot be measured because there is no such substance which will not remaining in plasma, which will not at all remaining interstitial fluid, and it will go into the cells only. Now suppose even if it goes only into cells and such substance has gone and sit into the cell, now how will you measure it? Because over here though it was easy, na? कि chalo, you have injected something into blood and then you take the blood sample out and measure. Easy. If the entire substance it goes into the cell, how will you measure? Right? Even if you have figured out with some substance that it goes only into intracellular, but then what? What will you do? It has gone into the cell. Now you cannot tap each and every cell individually and take that. Now that would be like a microsurgery, right? Not possible. So that's why we'll be using a very, very interesting, very simple logic. Very simple logic, and that logic is that our total body weight, total body water, right? Total body water is equal to what? Intracellular fluid plus extracellular fluid. If we can measure total, if we can measure ECF, problem is solved, right? Total body water, take it on this side, right? So total minus ECF, that will give ICF. Done, right? Trillions of cell, impossible to measure, yeah? It would be impossible to measure, exactly, right? So this is the concept. Once you have understood the concept, now we'll work on it. Now, before we start with that concept, let's see one more very interesting thing. And this will actually say make your understanding straight away to the next level. I am telling it that you know that, okay, there is blood, right? In blood, there is plasma, and then there is interstitial fluid. And normally we say, repeat again about plasma, means, okay. In any case, I'll draw it again, right? So let's not go back, we draw it again. So when we say extracellular fluid, right? Extracellular fluid. So that means this is the plasma, right? This is the plasma. In plasma, what is it? In plasma, that means it is into the blood, right? And this is like interstitial fluid, right? Interstitial fluid. And in between interstitial fluid, what would be this? Well, this is blood, right? This is blood. This means that this is a blood vessel. That means this is a capillary, right? And in capillary, between the capillary and the interstitial fluid, this is a very thin layer, right, which is called as the endothelium, right, endothelium. And via this endothelium, because it is a single layer of cells, right, things they ooze out, ooze in, right, they pass between plasma and the interstitial fluid. So technically speaking, both of them will be having very similar electro neutrality, correct? They will be having same electro neutrality. Make sense? Right? Because things can pass between both of them. That's why collectively we are calling them ECF, extracellular fluid, which is outside, the cell. Clear, Jaydev? Acha. So this is our interstitial fluid which is present between those cells. These are the cells, and in between is all that interstitial fluid. Now taking it to next level. If we means equilibrium is always maintained. Yeah, equilibrium has to be maintained. And if it goes bad, those 6 scenarios will explain, right? Those are the 6 scenarios which we'll be watching. 6 clinical scenarios. Now, this one is plasma, right? This one is plasma. Plasma means blood. Now, in plasma, you'll find that yes, there is water. But apart from water, say, you'll find that there would be sodium, right? Because there is some sodium even in the interstitial fluid, right? There is sodium, there is chloride into the interstitial fluid. Up to that point, the things are fine. That there is sodium, there is chloride, there is bicarb, but plasma is having something extra, and that is albumin. Albumin, right? This albumin is big one. When we talk about, say, interstitial fluid, can those 6 scenarios be applied to all cases? Yes, you'll be able to apply those scenarios in almost all the cases. In human body, somewhere, whenever there is pathology, somewhere at least one of the scenario would automatically be set. When we'll discuss, you'll find it. And in the interstitial fluid, right, interstitial fluid, because it is extracellular fluid. Extra means it is outer, outer means ocean, ocean means it has got large amount of sodium, right? There would be chloride, there would be bicarb, right? Yes, bus, stop here. Albumin you won't find in interstitial fluid. Theek? So there is something, because this albumin is negatively charged, huge one, right? Solid negative charged, right? So what about those? What will they really do? Because these are the large negatively charged proteins, right? So large and they are negative. If you want to impress, you can say anions. Now see what happens. We'll take a full page for it. And say this, and this, right? This one is plasma. This one is plasma. And this one is our interstitial fluid. Interstitial fluid. When it comes to, say, sodium, so sodium, right, they are Sharif going here and going here, right? Aram se they will cross each other, right, and they will maintain the balance. No problems, things are good. What about chloride? Yes, they can also tuk, right, tick, 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 right? They will go and come depending upon the concentration, they will balance. What about our albumin, right? This albumin. Now this albumin, when it would try to cross, right, he will be thrown back, because this is in between. Endothelium is nothing but a semi-permeable layer. It's a sort of semi-permeable layer. But its pores, they won't allow the albumin to cross. Albumin will remain on one side. Now this is huge one, big negative. So he'll say, अच्छा नला मुझे नहीं जाने देता, no problem. Now he'll start his role. What he'll say, अच्छा चलो, क्लोराइड नेगेटिव ना, नेगेटिव रिपेल, मारो इसको धक्का, फेंको, right? So it will throw the chlorine on the opposite side, right? Because see, he is big, He is negative. So he'll repel negative ions on the opposite side. So it will do one thing, repel negative ions on the opposite side. And दूर से it will attract those positive ions, those cations, right, from the opposite side, and attract positive ions. Yeah, you come here, right? How much this will happen depending upon the negativity of albumin. The final result is same. Electroneutrality. Electroneutrality. But in causing this electroneutrality, we cannot really say that it would be the same number of sodium in the plasma is equal to same number of sodium into the interstitial fluid. Correct? Because albumin, big negative which is standing, is grabbing the sodium on his side and throwing the chloride on the opposite side. It will keep on doing it till the electroneutrality is there. It is there, so then it is happy. Right? So there would be some difference. There would be some difference between both of them. Electroneutrality is maintained, but the number of ions into the plasma and number of ions into the interstitial fluid, they will vary to some extent. Perfect? Okay. If this is clear, then let's give it a name. They have given a name, right? And these are the names. Unfortunately, we have to remember, but ठीक है. Consider that someone who has done this thing for the first time, so we appreciate. So it is called as the Gibbs-Donnan effect. Gibbs-Donnan effect. Gibbs-Donnan effect tells that the large negatively charged protein particles, they will repel anions and they will attract cations till the electroneutrality is maintained. After that, nothing happens. Everything is fine. Right? So far, so good. Now we introduce our ICF. So here is the plasma, here is our semi-permeable membrane, and this is our cell, the intracellular cell. Does albumin need energy to okay? No, these are the channels, right? So it is a natural repulsion and attraction. Here energy won't be needed. Energy would be needed now. So this is a cell, right? This is a cell. Intracellular fluid or the environment is here. And this is where the potassium is present, correct? And who maintains albumin concentration? So many factors. It can also be for negatively gone beyond. Yeah. There are so many factors actually. So that's why what happens to albumin, what happens to globulin, right? All those proteins, how they increase, how they decrease. It's a completely different topic. But yes, there is a complete mechanism because albumin also, it cannot go haywire, right? To any number of, it can increase or decrease. No, it is not like that. It has to be maintained. Okay. The point over here is that there is large amount of potassium inside and there is large amount of sodium which is present, and they are going inside, coming inside. So there is a huge potential difference between extracellular fluid and the intracellular fluid, right? So over here, the plasma, we can say, is equal to interstitial fluid, right? There is very minor difference, otherwise they both are same. Collectively ECF. But between this ECF and this ICF, there is a big difference. And it is this big difference which leads to most of the physiological activities of electronics, right? What that electronics, what is happening, that would be because of this. And one of the commonest is sodium, potassium, ATP is active pump. Now, there is one very beautiful word for it. It is called as the ubiquitous. Ubiquitous means this pump is present everywhere. It is present everywhere. Right? It is like aloo, right? दुनिया में कहीं भी जाओ, you get the aloo. So that's why aloo is like ubiquitous. So this sodium potassium pump, anywhere you in the body you go, you will always find it, that it is always there and it is working continuously. Right? So with this basics, let's do the practical of dilution method, right? And then we'll study those scenarios. Now see, this dilution method is so interesting. I say that if you understand it, you will understand in 5 minutes, not even 5 minutes, right? It will take less than that. See what we do. Same figure, right? Truck, and here we just draw it for the sake of, right? This is endothelial layer, and that's our cell. Bus. Will not write anything, we understand, right? This is blood, right? So that's blood. Chalo. And now let's inject something. We inject. First we inject something which is easy to measure, and what we really want to measure, we want to measure our total body water, right? So what we do is we inject D2O, right? Because this is a radio labeled thing, right? So it would be measured into the form of curie, millicurie, right? So let's say we inject 150 millicurie of D2O. What would happen? This D2O will go into the blood. From blood, it will go into the interstitial fluid, right? And then it would also go into the intracellular fluid. That means it will go everywhere. It is distributed through and through into the entire body. Nice one. Next, we inject one more thing. This time, sorry, we inject mannitol, right? Small quantity. So not even 1 full gram, 650 milligram, right? We inject 650 milligram. Where would it go? It will go into the plasma. It would go into the interstitial fluid, but it won't be able to go into the ICF. It won't be able to go, right? So this means we are measuring in its simple terms, total body and the ECF. Okay? Let's proceed. So now from this point onwards, D2O, the total is like 150, and our mannitol is say 650. We measure the urine, right? After some time, after about 2 hours, we measure the urine. In the urine, how much D2O has been excreted? Because see, it is going everywhere, so it will also be going into the kidneys, and kidney will filter it, so it will be excreted into the urine. For our convenience sake, just for the understanding, let's say 10% is excreted, both 10% of both is excreted into the urine. So now that is out, right? That is out. So how much D2O now is present into the body? Well, 150 minus 10%, that is 15, that comes to 135 millicurie. This much is present into the body, right? Similarly, for the mannitol, it is say 650, right? And again, this is also say 10% is excreting. So we'll go for 650 minus, that's right? So 65 is going out, and that is giving 585 milligram into our body. Now this is into the total body, right? It is into the total body. So if we say that it is into the total body, so then what we have to do? we have to measure. We have to really measure 6. Acha, see, mannitol usually this much is not excreted. Uh, let's make a small change. Small change. 1% of mannitol is excreted. Right? We let it excrete only 1%. Yeah, because 10% would be too high in this much short span. By the time when 10% of D2O is going out, only 1% of mannitol can go out. So we have to change the calculation slightly, right? So change it slightly. Just a decimal would move. So this will be what? This would be 6.5. Correct? 6.5 because it is just 1%. So this would be like 643.5 inch. Now it is perfect, right? You'll see the effect on the final result. So this is in the body. In the body, this much is present. Now let's take the sample out, right? And we take the sample out and we measure, right? So sample of blood taken out, taken, and concentration measured. Concentration measured. So what we are doing, we take out by say 10 ml and then we measure that how much D2O and how much mannitol is actually present. So that is the concentration, right? And usually concentration will be written in per 100 ml. So we have taken the 10 ml out and we multiplied by 10. So this is the concentration what we are getting. Say D2O, let's say we are getting 0.32, right? It would be very less, 0.32 millicurie per decaliter or 100 ml, right? When sometimes if it is written DL, that means 100 liter, 100 ml. Mannitol, right? Again, it would be less. So say 4.6 is what we feel, 4.6 milligram again per 100 ml. With this, let's start our calculation. Right? First of all, we go for ECF, extracellular fluid. Right? For the extracellular fluid, we have to use what? We have to use mannitol, correct? Because extracellular fluid, it was not going into the cells. So that would be our mannitol. What was? We said that the total amount upon concentration, correct? So how much was the total amount? The total amount was 650, but because this much got excreted into the urine, so that's why what is left out is 643.5, correct? So 643.5 upon. How much is the concentration? Well, mannitol, this is the concentration, right? 4.6 mg, right, per 100 ml. So just calculate, right? 643.5 upon 4.6. What's the answer? 643.5 upon 4.6. So roughly divide by 5. So it would be around about 140. 140. 4 4s are 16, right? Roughly. So anyone can calculate. 643.5 divided by 4.6. So that comes to, should I take the calculator out or you write? Anyone? Roughly it would be around 140. Okay, it is 139.8. 139.8. This is per 100 ml, right? We have to, this is for 100 ml. We have to calculate it in 1 liter. So we just shift one decimal. So this is 13.98 liter. Correct? Because this is upon 100 ml. So this will go up. So over here it will come 100 ml and we want it for 1000 ml, right? So this is 13.98 liter. This 13.98 liter is our extracellular fluid. Nice one. Now we calculate the total one, right? For total body water. So for total, we'll be going for the D2O, right? Again, the same principle. What's the total amount upon what's the concentration, right? Our total amount in case of D2O, that was 135, and 135 upon 0.32. So 135 upon 0.32, right? Units are millicurie per 100 ml, right? Millicurie per 100 ml. So this is coming to what? 135 upon 0.32. Right? What the number comes, that is for 100 ml, and we'll shift one decimal to make it for the 1000 ml or 1 liter, right? What's the number? Just let me know. Right? So whatever the number comes, this is giving us the total body water. Right? Anyone who has calculated, just let me know. And once we have got the total one, right? Total. So this total body water minus our extracellular fluid becomes intracellular fluid level. That would become the ICF. How do we get concentration D2.3 and mannitol 4.6? By measuring, because you have to take the sample out and then you have to measure the concentration, right? There are various methods of measuring the concentration. Right? 422. Okay, so 422, and for 1000 ml it will become 42.2, right? So 42.2 liters, that would be the total body water, right? 42.2, that would be the total body water. So all you need to do is you have to just subtract and you have to get the final answer. So total 42.2 minus ECF, which was 13.98, and that will give the value roughly round about 28, right? So this is your total, this is your ECF, and this one is your ICF, intracellular fluid. 421.875. ठीक है. So here also there would be some decimal, but otherwise 42 minus 13 makes 29, and then yeah. So we have assumed the measure. Yeah, over here right now we have just taken the value, but otherwise practically you can measure it, right? But yes, right now for the sake of understanding, we have assumed those values, but they are very near to normal, right? Normally also you'll be getting these values. Okay, so this is how we really measure the ICF. What I wanted to emphasize was that there is no indicator which will be measuring only the ICF. What could be the reason to inject D2O and mannitol with different concentration? Why not same? Well, you can inject the same, but well, it won't matter much. Things are injected on the basis of, because you have asked this question, right? There is no need to inject both the things of the same amount. Why? Why should we inject? We should inject, say, because it is D2O, it is measured in the form of millicurie, right? Millicurie. This is a radio labeled, this is a radioactive substance, right? This is a radioactive substance. This is the same question if I ask that, Deepak, do you really like chai, asli, tea, chai, right? So can't we do that, say milk, water, chai ki patti, right? Because there is no English word for that, chai ki patti, right? And the sugar. Let's add all of them in exactly the same proportion, right? Exactly in the same proportion. We don't do that, right? Because everything has got its own characteristic. Similarly, D2O and the mannitol, right? They both are completely different substance, right? So ECF of mannitol, what about ECF of D2O? It should also be calculated and then subtracted. Why? Say ECF of mannitol, right? ECF of mannitol, extracellular fluid of mannitol, and ECF of D2O. First of all, mannitol, right? Mannitol, when it is in ECF, against the entire body fluid, that 650 milligram is negligible. So we don't have to calculate, we don't have to adjust for that, because it is just too minor, right? Too minor. So you got the idea that we are actually doing, right? We are actually doing, when we are going for D2O, D2O is measuring the total fluid of the entire body, है ना? And mannitol is measuring the ECF, right? Because it cannot enter into the cell. So that's how, and this is in mg. So that's how things are there. Now in radiology, when you do angiography, right, sometimes you inject the dye which is in just few mLs, but when it goes inside, the yes, how much luminance it is creating, right? And then, but at the same time, some iodine based dyes, now you can't give it at your will, right? Iodine based dyes, because they have got some toxicity also, right? So they have got the toxicity. So that's why you have to control, and that's why the doses have come into picture, that even when you inject the dyes, even when you inject these things, there are specific doses which are permissible. Beyond that, there would be toxicity. So that's the part of pharmacology. So in pharmacology, you learn these things, right? Say when it comes to radiology, when you'll be talking about all the dyes which are injected for various purposes, various procedures, every dye, it has got some toxicity depending upon its iodine content, depending upon its nature. So you have to actually test the patient also, so that nothing wrong goes. How do we measure the concentration? Is this will be taken in practicals? No, no. This is for understanding, right? Practically, I doubt if anyone can do that. Right? It is possible. It is not at all difficult, but this is for the understanding. Regarding measurement of the concentration, there are various methods. They can be measured with the help of spectroscope, right? Even it can be measured chemically, so many methods. And for the radiology, for the radio part, that is radio label thing, so there are gamma scintillation cameras, right? So far, we learnt one thing, that interstitial fluid, right? That is fine. But for the pure intracellular fluid, there is no indicator available. Yes, barium dye, that is in esophagography, that is barium swallow, right? When the patient gives you dozens and dozens of galleys, because you have to tell the patient that, okay, that paste like, right, when it is a white colored thing, what is the name of the gel applied during sonography? And that is the use of that gel. Well, that gel, right? That gel, when it is applied, it actually it creates the it removes the air in between, right? So that your probe is directly in contact with the skin. And what I was talking about, the barium, right? That barium swallow, it is like a thick paste, right? And you tell the patient, "Kare muh mein rakhna," and when I say, okay, swallow, and it is at that point when you start taking the X-ray, and then he swallows, giving you dozens and dozens of galleys because it is so bad, right? When you want to take the stomach, so then it is, right, it is the barium swallow. Then there is a barium liquid, then there is barium meal. Barium meal is not that okay, make that toast of barium, right, and if possible just grill it. No, it's not like that. Patient has to drink glasses and glasses of barium, and then as it goes through the intestines, you are taking pictures one by one. Pictures means you are taking the X-rays one by one, and you are examining radiologically. So that's how the barium really works on. So this was the thing, the total body water, or in case, say, this is one important criteria, that total body water. In case of males, right, it is more as compared to females. The reason, this is inversely proportional to the fat. Remember, it is inversely proportional to the fat. Now when you calculate, it is like every female, right, every female, if your weight is somewhere between 55 to 60 kilogram roughly, right, so it has to be at least 2.2 to 2.5 liters of water is compulsory. For a male, it comes to about 3 liters of water a day. This is really very much needed, right? It is really very much needed. Now this water, it is not so that it is present only into these areas. There are few, what we said, that interstitial fluid. Interstitial fluid means with something which is outside the cell, right, just between the cells, between the cells. So such special fluids, right, these are some special ECF fluids, extracellular fluids, right, ECF fluids are the whose function depending upon the area, right. Say for example, in case of brain, you will find CSF, cerebrospinal fluid, right, it is into the brain. Now its function, protection and the nutrition, it acts as a buffer, right, very vital. Say in case of joints, we are telling since long synovial fluid, right, which is acting like a gearbox. So here its function would be the lubrication to prevent the friction, right. When it comes to heart, heart keeps on pumping, but surrounding the heart there is pericardial fluid. So peri means surrounding, cardial means heart, so there is a pericardial fluid. And then there are dozens of pathologies which are associated with pericardial fluid, right? Because when there is fluid, that means these fluids, they are not dead fluids, these are not stagnant fluids, they keep on changing, right, they keep on getting absorbed, new fluid keeps on coming, right. Say in case of eye, right, there is aqueous humor, right, aqueous humor, right, in our eyeball. And in case if there is any change in this right, in this fluid, so if it increases or it decreases, so many complications, right. Then in case of lungs, so the lungs are surrounded by pleural fluid, because those pleural cavity, and in between, right, there is pleural, there is visceral pleura, there is parietal pleura, and in between there is fluid. So that fluid is generating that pressure, and both the things, they are with the negative pressure, they both are attached with each other. That is what keeps the lungs inflated. If there is any air goes inside, to immediately the whole lung collapses, right. So that's why this pleural fluid, it has got superb functions, right. So that's the point, that all of them, they are of such vital importance. Okay, we now move on to our, can increase in CSF affect your field of vision? Yeah, it can, because if the CSF for some reason, if it is increased, it can increase only when there is some block, because fluid is constantly getting produced, right. And if there is some block, so it will lead to raised ICT, raised intracranial tension. When the intracranial tension, when the in the skull, when the pressure rises, that is called as the raised ICT, raised intracranial tension. So first thing, it will lead to headache, right, it will lead to headache. So that is very important, right. Visual disturbance, right, there would be giddiness, right, chakkarana, and then the blood pressure starts rising, all these things, right. Intracranial tension, that is what it, yes, it can affect the visual disturbance. The reason is because it affects it generates pressure, and the optic nerve starts affecting. In stomach also there is fluid. In stomach, the fluid which is over here, right? This fluid, this is for the digestive system, right? This is for the digestive system. Yes, in that there is vitreous humor also, right? Aqueous humor was just, and that's the, is that what caused glaucoma? Glaucoma is raised pressure into the eyeball. Yes. So that's why when this fluid is also, even in eyes, right, that fluid, it keeps on getting formed and keeps on getting absorbed. So if there is any block, so yes, that leads to glaucoma, right, when the fluid pressure is raised. And higher fluid pressure, that can lead to even the blindness. So that's right. On to our next topic, and before that we just understand what is a very simple thing, osmosis, because it is this osmosis which will lead to superb 6 scenarios, right? Every scenario will take just 2 minutes to understand. Stomach fluid, there is fluid in the stomach. Maybe you are talking about peritoneal fluid, right? In the entire abdomen, the way you have got, I got it, what you are telling, right? The way we have got pleural fluid surrounding the lungs, right? In the abdomen, right? In the abdomen, I got it. It is called as the peritoneal fluid, right? Peritoneal fluid. Got it. So now in osmosis, we take water and then let's put one almond in it, and we let it remain. Next morning when we see, we find that that almond has become bigger, right? And it has soaked so much of water inside, right? It has become soft and so much water has come inside, right? Water has moved in. Remember this principle. In osmosis, every time, whatever happens, same thing is true even in our body. It is the water which is moving. It is the water which will move. Bus. Through any of the compartment, only water would move, no one else, right? And all the game, yeah, and all the games, they will be starting from that point onwards, right? So that's what we say when the water moves. So technically speaking, how it happens, that if I make it slightly like this, is a semi-permeable membrane, right? We try to be very scientific. Semi-permeable membrane, right? See, there is one scientific method and there is one very desi method to remember this, right? We always go by a very desi method, right? We'll speak scientifically, but in the dimag, it will be going like, okay, this is more or this is more. This is what will happen. And then we use scientific terms. Actually, for all 6 scenarios, we'll do that, right? But the only portion what we speak in our language, right, we'll keep it in our mind, right? Don't speak in viva. Don't speak in front of anyone. Speak in front of everyone the scientific words, right? So we'll consider both. Okay. So here it is, the scientific way, right? We are going scientific, right? So let's fill this thing with water. Okay. So both are filled with the water at the same level, right? Same level. There is a membrane in between, and we add salt, 1 teaspoonful or 2 teaspoonful of salt. So salt is here. Osmosis is nothing but water. It is the water who is the decision maker. Water would say on the opposite side, this side is A, this side is B, right? A would call B that how much water you have got, right? It will say, okay, I have got, say, example, right? I got 1,000 units, right? A would say that I also got 1,000 units. But is it same, right? This salt would say, acha, right? In that one of the bakwas ad, right? They say, acha, आप मुझे तो भूल ही गए, मैं अभी ये you know what, which advertisement I'm talking about, right? आप मुझे तो भूल ही गए, right? So this salt would say अच्छा आप तो मुझे भूल ही गए, right? हमारा दिल भी यही है, right? So that is, so it will say कि my 100, count my 100 also, right? So this is where this would say कि ठीक है, I am 1000 but my concentration is low. Got the point? Concentration is low. Because against 100 units of salt, there are 1000 units of water. While over here, let's say there is 10 units of salt, right? थोड़ा सा salt यहाँ पे भी डाल दिया. So here there are 10 units. So concentration, relative concentration of this is high, right? So this higher concentration will say, chalo, let's move on to the opposite side, right? So that we want to neutralize this 100 units of salt. So wherever the salt is more, that means relatively less water is there, relatively, right? Relatively, because salt is more. So opposite side, where the water concentration is more, it will start moving and the water will move from B to A, right? See the example. This is how we understood scientifically. What happened into that badam, right, in that almond? Surrounding there was so much of water. Surrounding there was so much of water. There must be some water even inside. But inside the almond there are so many electrolytes, right? It's full of electrolytes. So there is relatively less water. So in order to neutralize those electrolytes, those salts, right, the water would start moving from out to in, right, till the concentration of both becomes same, right? So that's why that almond swells. Almond swells. Am I clear? This is what is called as the principle of osmosis, right? This is called as principle of osmosis. So whether it is you add the glucose or you add sodium, for water, it'll say for me everything is same. I just have to calculate that what is the osmolarity, right? It will say. Now how it calculates? It will say higher concentration to lower concentration of water, because it is the only water who will be moving and no one else will be moving. So for water, everyone is same. It will say whether you are sodium or you are potassium, for me you are same. I consider you as one ion, right? Whether you are sodium or chloride, for me you both are same, right? Okay, so it will be considered as same. So ion, it is the ion. Ions, they are calculated. One ion, that is 1, right? 1. So how it goes? Say glucose. Glucose is non-ionic, right? Glucose is a stable one. So it will be considered as 1 osmole. 1 osmole. That is the unit. If you say Cl2, so it will say, okay, Cl2, you are not 1, you are 2, right? Cl minus, Cl minus, right? So you will be considered as 2 osmole, right? When it will say Na plus, so you are just 1, Na plus, so you are like 1 osmole. Simple, right? Okay, now let's take one example and that will make things very fine. You have to just answer this question, right? Here is the water. Osmolarity is always measured in liters, liter, right? So in this water, this one would be our substance, right? And osmolarity, because there is something like osmolality also, right? So remember, osmolarity. When we say osmolarity, it is basis of per liter. Per liter. Osmolarity is per liter. Easy to remember, right? Lality is on kilogram. right? So this is, right now we won't confuse between it. This is per liter. So here it is. Water is how much? 1 liter. Okay, right? And we have got glucose. So what would be the osmolarity? We said that glucose is non-ionic, so it is 1. ठीक? Easy. 1 liter. Sodium chloride, our normal salt. Sodium chloride, it will say, okay, sodium, you are plus, chloride, you are 1. 2 ions, 2. Good. 1 liter, again 1 liter. This time, 2 NaCl and 2 glucose. 2 glucose. So here it would calculate 2 glucose. Glucose, you are 1 and 2 units. So, okay, you have to buy 2 tickets. And sodium chloride, you both are 2, 2 each. So 2 into 2, 4. So this is 4, 4 plus 2. This is like 6. Are you getting it? Glucose is non-ionic, so that's why it has got 1, because we are using 2 units. So that's why we are making it 2. So similarly, in 1 liter of water, when we start adding number of substances like 4 plus 2. And now when answer this question, say we make a nice khichdi, right? Sodium chloride, we add glucose, and to that we add calcium chloride, and to make it still, let's say 3 3 4 2, 3 4 2, right? Now what would be the osmolarity? What would be the osmolarity if we have added this much into 1 liter of water? What would be the answer? Calculate. Okay, 14, 12, 16. Okay, so answers are like 14, 12, 16. 16, 16. How much weeks physio will go on? Well, it will go, it will take. And yes, I think I received your mail also this time. Yes, we'll try to take as much as physio as possible. Oh, someone with 18 also. Okay. Okay. Let's calculate. Let's calculate. Say this is 2, right? Sodium and chloride. So 1 plus 1, 2. 3 2s are 6. So this is like 6. Right? Glucose is 1. So this is 4. So this is 4. This is Ca, Cl, Cl. Right? So here it is 1, 2, 3. 3 2s are 6. So this is 6. Am I right? Right? 1, 2, 3. 2, 3, 6. So this is 6 plus 6, 12. 12 plus 4, 16. And this should be the answer. That's right. So all of you, 16. Great. Good one. Good one. I know. I understand. Right. Okay. So now you know very well about what is osmolarity. Now let's start with those 6 scenarios. And those 6 scenarios, once you understand, you'll be so happy with yourself. Seriously, I'm telling you, you'll be very happy with yourself. It will take just 2-3 minutes, but every time I'll be asking you 4 questions and you have to answer those 4 questions properly, right? In another salty solution, it will now shrink and come back to normal size, or could go plasmolized. Well, it will depend upon the concentration of new salty solution, right? What would be the concentration? Now, if the concentration of that new salt, right, it is more salty, right? It is more salty. So then what would happen? The water from inside will come out. So then that almond would shrink. That almond would actually shrink, right? That's right. Acha. Technical terms, we'll take it later, right? We'll do it in this way. First, the basic principles, right? Basic principles. But these are the three principles, and all you understood about ECF, ICF, intracellular fluid, extracellular fluid, interstitial fluid, plasma. Think about all those concepts and you have to answer these questions. Just remember these basic principles. One, when we add or when we remove any fluid, when we say okay, there is a fluid loss, right? Person is sweating, means while running marathon, right? There was heavy sweating, fluid loss. But that fluid loss, or when we drink, that fluid intake or in or out, it is only ECF, extracellular fluid, always, right? Because when we drink, it will go into the stomach. From stomach, it will be absorbed into the, say, intestines, and from there it will come into the circulation. When it comes into the circulation, it's what it is, ECF, right? It is going into the cell at a very late stage. Initially, so it is ECF. We are injured, right? Some injury, blood is going out, ECF is lost, right? Second, it is the ECF, extracellular fluid osmolarity, right? Extracellular fluid osmolarity, which will govern or which will decide the shift of fluid. Shift of fluid. So if osmolarity of ECF, extracellular fluid, is more, so then fluid will shift accordingly. If it decreases, the fluid will shift accordingly, right? How it shifts, we'll see. Correct. The third one, third and last point to remember. This shift, it always occurs between ECF and the ICF. And it will continue, this shift would continue till neutrality is achieved, right? Till osmolarity is same. So it's like that almond won't keep on going bigger and bigger and bigger and becomes as big as tarbooj, right? As big as watermelon. No, it won't be that big, right? The moment osmolarity is balanced, but it will stop at that point, right? So this shift of fluid would continue till that point. So with this much, right, now we are ready to understand all the conditions, right? Every time we'll be using exactly the same figure, right? Same figure. And we'll draw it like this, because we know that ICF is more, right? ICF is about 2/3 and ECF is about 1/3, right? There is a semi-permeable membrane over here, right? So where the fluid can go and come in, right? And when we are drawing this, it means it is indicating us the volume, right? This is like a volume, right? So we are dealing with so we have got four things to consider. One, volume of ICF, volume of ECF, osmolarity of ICF, and osmolarity of ECF. Fair enough, right? This is what would happen. See, these questions which you are asking, they will totally deviate from our normal topic. So that's why we are not taking those questions right now, right? You can send a mail. You can send a mail, because otherwise we won't be able to not only finish this, the whole audience would be deviated. So let's focus on now first these 6 conditions, because these are very vital conditions. So here is our first condition, right? So our first condition, normal body, right? Normal body, and we add isotonic solution. We add isotonic solution. Isotonic solution is what? Normal saline, right? Normal saline. When we say normal saline, that is 0.9% of sodium chloride, right? This is what we give. So it means it is what? It has got salt, it has got water. We are injecting these things into the body. Why this 0.9%? Because this is exactly the same proportion as it is found in ECF. Sorry. This is the same proportion what we find in ECF, right? Extracellular fluid has got almost the same proportion as that, right? Now see what would happen. This is the figure which we draw, right? We draw this. Here, this is intracellular fluid. Sorry, this is extracellular fluid. We are adding the extra fluid into our ECF. This is the extra fluid which is added, right? Extra, you are getting it? We are adding the extra fluid into the ECF. Every time we'll add it into the ECF only, correct? So this is ECF, this is ICF. Volume. First question. ECF volume would increase or decrease? Obviously, it would increase, right? It would increase because we are adding the physical volume into the body. We are injecting it into the blood. So straight away, new thing is getting added into the ECF. So obviously, ECF volume would increase. Volume would increase. Will there be any change in the osmolarity of the ECF? Well, the fluid which we are adding, it has got the same osmolarity as that of ECF. Got it? It is the same osmolarity as that of ECF. So relatively, we take 1 chai ka cup and in that we are adding 1 teaspoonful of another chai. But the amount of sugar, right? The sweetness of 1 chai ka cup and sweetness of that 1 chammach chai, if it is same, so there won't be change in the any taste. There won't be any change in the taste. You're getting it? 1 chai ka cup and another small chai ka cup. But if the sweetness is same, if this is 100 ml, this is 50 ml, in 100 ml there is 1 chammach chai, sugar, in 50 ml, if it is half chammach, you mix both of them, taste will remain same. So that means osmolarity will remain same. There won't be any change. If the osmolarity of ECF is same, again, they are notorious. Okay. So if the osmolarity is same, right? So then what would happen? Nothing. It is the osmolarity of the ECF which determines the shift of fluid. So it means in this case there won't be any shift of fluid. So ICF will remain as it is. So this is same, and because fluid is same, so even there won't be any change in the osmolarity of ICF. Is this clear? Because this is the simplest of the explanation, right? Now we'll start making the changes into it because this is a normal phenomenon. This is what you'll be doing in clinics. You have say one patient and you find that his body is almost like a dried up, right? He's and this is what is called as the hypovolemic shock, right? So you simply start the normal saline. The moment you start with the normal saline, and you'll find that yes, he is recovering. That his blood pressure was falling because the amount of fluid into the body was less. So you are giving the same type of fluid what the body has got. So its blood pressure will start coming back. So this is what this isotonic solution, this is what is called as the 0.9% sodium chloride or the NS, normal saline. This is what is given in hypovolemic shock. Hypo means less, volemic means where the volume is decreased, shock means it is that condition when there is loss, right? When the body, it is a state of emergency. Shock itself is a huge topic, fantastic topic, right from the hemorrhagic to all types of shock, right? So this is done. Let's move on to the second condition. Now this time you have to really think, right? So this is now condition number 2. Condition number 2. In this condition, we are adding, right? We add this time hypotonic solution. Is such solution available? Definitely available, right? Say instead of 0.9% sodium chloride, this time we are giving half strength normal saline. So that is 0.45% sodium chloride. So what does this mean? This means, see, technically, right, in very crude language we understand कि अच्छा boss, this means कि you are giving less salt and more water. ठीक? This is what you are doing, right? This less salt and more water with respect to ECF, with respect to our extracellular fluid, right? So that is what would happen. So we go back to our image, right? We draw it like this, and this is our, say, extracellular fluid, and this is like our extracellular, and this one is the intracellular fluid. So now when we are adding, right, we have added something to it, right? But what would happen over here, right? What would happen? First thing, right, we draw it like ECF, ICF, volume, and osmolarity. Because you are adding some fluid, right? So definitely there would be rise in the ECF because you are injecting things into the ECF. ठीक? So this is increasing because we are adding the fluid, correct? Now when we are adding the fluid, after adding that fluid, what would happen to the osmolarity of ECF? It will increase or decrease? Because see, we are adding more water and less salt into this unit. So it is like, think of that chai, our chai ka ek cup, right? We want to add some more chai to that, but this new chai is peaky. It has got less sugar. So if we add that peaky chai to our normal chai, our new chai will be more sweet or less sweet. Am I getting it? Are you getting it? So that is the osmolarity. What is the relative salt into less? Exactly. So osmolarity would decrease. Our chai would be more peaky. Right? Now it is this osmolarity, it is this who is deciding the fluid should shift where. Immediately it would say that we have got less salt over here and we have got more salts. This is a relative thing, right? Less salt. So it will say कि चलो, less salt means less salts. Less salts means more water, relatively more water. It will say चलो ECF start moving towards ICF, right? वहाँ पे ज़्यादा salts हैं, neutralize them. And there would be shift of fluid from ECF to ICF. What would happen? ICF, intracellular fluid, that would rise because fluid is coming from ECF to ICF, very right. So there would be rise in the volume of ICF. Perfect. Now from the ICF perspective, ICF was having its own chai and now we are adding water into it. So that chai will become peaky or that chai will become more sweet. Correct? Are you getting it? Because ICF has got its chai. So, but now we are adding just water into it. We are not adding any sugar into it. So that Fiki, exactly, Fiki, right? Perfect. So thus there would be decrease in the osmolarity of the ICF. Literally, always remember it like this chai concept, right? Don't speak to anyone, But when it comes like that, and then it would really look very impressive, है ना? Because when you say that when we add hypertonic solution to the ECF, obviously there would be decrease in the osmolarity because there is relative less, दिमाग में आया less चीनी, but we said because relatively there are less salt, more water, and because the ECF osmolarity is something which is governing the shift of fluid, the fluid will shift from ज़्यादा मीठी चाय to less मीठी चाय. हाँ, so it will go from say ECF to ICF, and then ICF की चाय फीकी हो गई. So thus ICF osmolarity will go down, but because सादा पानी ऐड किया था तो चाय का कप थोड़ा बड़ा हो गया, ज़्यादा हो गया. So ICF volume would increase. Right? Done. You never go wrong. Right? चलो. Now to next four examples. Next four examples, it would be like a cakewalk. Within seconds you will be answering. The third one, right? This time we add hypertonic, right? So we add hypertonic solution. Hypertonic solution means we simply understand that it has got more salts. So it has got more salts and it has got less water, right? And who remembers it like this? Remember our chai ka example, right? In this chai, this is now we are offering a chai with 10 chammach chini, right? So draw our figure. Here it is, our ICF, our ECF. To this ECF, we have added, right, a very, very, very sweet chai, right? So now our standard four questions, right? ECF, ICF, volume, osmolarity. What would happen to the ECF volume? We are adding something, so ECF volume would increase, right? We are adding such a meaty chai, so our original chai will become more meaty than the previous one. Sure, right? So that's why osmolarity would increase. Correct? Very nice. This osmolarity would increase. So technically speaking, what this means, there are more salts, right? There are more salts here, and less water, and here there is more water, right? Exact opposite. Very right. So now where the movement will start? The movement will start from, yes, you have already, Jaydev, you have written ICF to ECF. Very true, right? Water from ICF, because it is the only water which can move. So it will move from ICF to ECF. So it in that way, ICF volume would decrease. Got it? ICF volume would decrease. And what would happen to the osmolarity of ICF? What would happen? Now, what would happen to the osmolarity of ICF? What would happen when the water from ICF has gone into the ECF? Think, yeah, this is trick. No, Jaydev, Aishwarya, think it like this. Wait. Don't answer. Wait. अपनी chai, right? First, our chai was sweet, right? Normal. Our chai was normal. Now, if you take water out of it, so that chai will become more sweet or less sweet, right? It will become more sweet because you have taken the water out. So it will be ekdam mast, ekdam solid, concentrated, and that is increase in the osmolarity. Very right. Because number of salts, relative number of salts, they will be much higher, right? This is the trick, right? Remember this. Because when the water is leaving, so that means यहाँ पे इतने सारे salts. Now water has gone, तो यहाँ पे इतनी सारी चाय, इतना सारा sugar, so obviously it will be more sweet. When the water comes, it dilutes. When the water goes, it concentrates. So this is what really happens. Now we take clinical condition, right? These were the things when we were giving some fluid, right? So we took three conditions in which we were adding, we added isotonic solution, we added hypotonic solution, and we added hypertonic solution, right? Now you must have guessed. This time we'll remove, right? So any condition of the body, it would fall into any of these six category, any of the medical condition. Either there is loss of fluid or there is gain of fluid, right? Iso, hypo, and hyper. Perfect. Okay. So now condition number four, right? It would be four. Yeah, it would be four. So this time, loss. Loss of what? Loss of isotonic fluid. Loss of isotonic fluid. How can the fluid be lost in such a precise manner? Very simple. Injury and the blood is going out, right? So when the blood goes out, blood will go in its full form. Means cells will also go out, right? Electrolytes will also go out, fluid will, plasma cells, everything will go out. So that is, say for example, hemorrhage. So it is exactly same fluid which is going out, right? Now see what happens, right? Our standard figure, right? And our standard question, ECF, ICF, volume, and osmolarity. This time it's a loss, right? This time, remember, it's a loss. So fluid is decreasing. So this is the ECF, this is the ICF, right? Fluid is decreasing. When the fluid decreases, so obviously the volume of ECF would decrease. Very simple, right? What would be the osmolarity? What would be the osmolarity? Osmolarity of ECF. What would be the osmolarity of ECF? What would be the osmolarity of ECF? Say no change. Perfect. No change. It's like out of 5.5 liters of blood, we have donated some blood, right? But the blood was donated, it was isotonic. So there won't be any relative change into the osmolarity. So nothing would happen to our cells, right? So after blood donation also, we are completely fine. So this is same. It is the osmolarity of ECF which decides whether the fluid would shift or not, but because it is same, so obviously there won't be any shift of fluid or there won't be any change in the osmolarity of ICF, right? Nothing to do with osmolarity because it is a loss only. That's right, it's a loss only. The same type of fluid is getting lost, right? Same type of fluid. The whole blood is getting lost, not something particular. Great. So this is same and this one would also remain same. Good. Now you are understanding very properly, very, very properly. So say for example, in such case, hemorrhage, right? You find that there is hemorrhage. So what would you do, right? In the treatment, what would be the first thing you'll advise to this patient? What would you say? Okay, sister, start what? What would you start? Which solution you will start so that this loss of ECF is taken care of? What would you start? Stop the bleeding, iron, saline, isosaline, right? Isotonic saline, very right. Because we know that isotonic saline, what it would do? We go back. Right. See, isotonic saline was doing what? Isotonic saline was increasing the volume of ECF. Correct? Because it was getting lost. So that is now corrected. So done. Everything fine, right? Patient will come back. How patient would really present in this case? Because the volume is lost, right? Because the volume of the blood is decreased. So there would be decrease decrease in the arterial pressure, decrease in the arterial pressure, you will find that his blood pressure is dropping, right? Blood pressure is dropping. So this would be a great indication. And as soon as you'll start saline, you'll find that blood pressure is gaining back because the amount of fluid is increasing. So pressure is what? Pressure is, blood pressure is what? It is the pressure exerted onto the walls of arteries with every thrust. So now the volume is sufficient, so it will come back to the normal pressure. Perfect. On to the fifth condition. Chalo. This time, so condition number 5. This time, loss. And this time we go for the loss of hypo. Sir, but what if the amount of bleeding is greater than saline infusing? Well, that's a trouble. Then that's a trouble. As we said, that if the bleeding is more beyond certain level, so then you have to not only stop the bleeding, but you need to even give the blood infusion, right? Because every time only saline is not sufficient. It will take care of this pressure part, but the blood is important because it will be carrying the oxygen. So that's how that immediately, so you'll give saline, but then you have to replenish with the blood infusion, right? And obviously higher bleeding, so after certain time, we have discussed it, that it goes for that vicious cycle and there is no choice which is left out, right? Okay, so loss of hypotonic solution, loss of hypotonic solution. Rupture of major artery, so then you don't have even that much chance, because if the major artery is damaged, so the blood goes out at such a high pace that it becomes almost a lost case. Achha. So hypotonic solution, right? Hypotonic solution, where would it occur? Now, to explain this, I need to take you to a small journey, right? We know about diabetes, right? Diabetes. There is diabetes mellitus, right? Mellitus means sweet. Why it is sweet? It is because the sugar which is going, right? Sugar is going out into the blood, into the urine, right? So that is diabetes mellitus. There is another diabetes which is called as diabetes insipidus. Insipidus means tasteless. Tasteless. Because in this, there is loss of water. Loss of water, right? So loss of water, loss of plain simple water. This occurs because in brain, right, there is a nucleus called supraoptic nucleus, right? It is called a supraoptic nucleus. Now, what this supraoptic nucleus does, it releases ADH, that is anti-diuretic hormone, right? Diuresis means let the urine go, right? Don't call it back, right? So this is anti-diuretic. So it would say, no, body cannot keep on losing the water like this. So it is this anti-diuretic hormone which will tell the kidneys, take this water back, it is needed. You can't just keep on throwing the water without any reason, right? This ADH, anti-diuretic hormone, there is another name also, it is AKA, also known as vasopressin, right? It is also called as the vasopressin. Vasopressin, right? So this is a normal phenomena, right? This is a normal phenomena, and in other words, it saves water, right? It saves water because water is absorbed, reabsorbed, it is taken back into the circulation. Whenever there is ADH insufficiency, which occurs in cases of diabetes insipidus. So in ADH insufficiency, what would happen? Large amount of plain simple water is lost, right? So plain simple water is lost. It has got nothing to do with electrolytes. So simple plain water is going out. Obviously, this simple plain water which is going out, it is from the ECF, right? So here is our situation, right? This one is ICF, this one is our ECF, right? And our questions, the volume, osmolarity, our ECF, and our ICF. So in ECF, obviously there would be loss. So there would be decrease in the volume, right? Only the water is is getting lost, right? We are losing only water. What would happen to the osmolarity of ECF? Water lost, right? Water lost in our chai, right? The standard chai, same chai, right? But now the water is has been taken out. So now this chai will be fiki or it would be strong, right? This is the water is lost. Simple plain water, simple water is lost. So what would happen to our chai? Yes, exactly. It would increase because relatively water has gone out, so it will become more strong. That's right. So this means there would be increase in the osmolarity of ECF. Perfectly fine, right? So the moment we see here कि अच्छा osmolarity has increased, so that means something would happen. Something would happen. Some fluid shift is going to happen. All we need to decide is where are more salts. Now osmolarity increased, so here there are more salts, right? So wherever there are more salts, the water from the opposite side दौड़ता दौड़ता आएगा कि चलो मैं आपको neutralize कर दूं, right? That is what is going to happen, and water from the ICF will come on the ECF side. Perfect, Jaydev, very right. So ICF to ECF movement will start, right? This is the shift of fluid from ICF to ECF. That's right. So there would be decrease in the ICF volume. Perfect. Very nice. Now when the water has shifted from the ICF to ECF, what would happen to the osmolarity of ICF? What would happen to our chai in ICF when the water has gone out? It will increase. Very good. It will increase. See how good you guys are, right? Not a single mistake you are doing. Perfect, right? This is what would happen in case when there is diabetes insipidus, right? Okay, moving on to the sixth condition. And see, when actually you'll be learning that endocrinology, right? When you'll be learning about say diabetes insipidus, and when you'll be we'll study one more case of Addison's disease, right? So when you'll study, these things will come in your in your mind, right? Like a movie. And in book you'll find that paragraphs and paragraphs are written, right? There would be increase and decrease in the osmolarity. It's so crazy. It's so crazy, and it becomes so difficult to remember. Trust me, you revise this thing very properly for 2-3 times bus, right? I'll show you a method also of revision, that how to do it, right? You have to just make a table, right? And stop reading for say 2 hours, and then condition 1, condition 2, 3, 4, 5, and increase decrease, same, right? Just fill all the things and then check it out. But do this thing 2-3 times and you never have to worry about these things anymore, right? And this chai, right? Still, I always explain by this method of chai only. That's right. So let's start with sixth and final condition, that there is loss. This time we want that there is loss of hypertonic solution. There is hypertonic solution that is getting lost. Hypertonic means what? More salt, right? More salt. So more salts are going out, less water. Sorry. So this thing happens in what is called as the mineralocorticoid deficiency. right? It is mineralocorticoid deficiency. What it really does is it balances or it regulates the minerals, right? So this is also called as the Addison's disease. Right now we are not entering into the details of this Addison's disease, but we just understand that in this disease more salts are lost. That's right, you're right. More salts are lost, right? So coming back to our figure, this is ICF, this is ECF, and our ECF, ICF, and volume and osmolarity. What is happening? We are losing more salts and the water. So what would happen to the volume of ECF? Well, we are losing, right? Even thoda to thoda, but water to is getting lost, right? So there would be decrease in the volume of ECF because there is a loss, right? Very right. Chai will be fiki. Perfect. So that means there would be drop in the osmolarity because more salts. चीनी ले गए इस बार तो, है ना? They took away the chini out of that chai, right? चीनी निकाल के ले गए. So obviously the osmolarity is decreased. Very good. So it means there are less salts over here. So if there are less salts over here, there would be relatively more salts on the opposite side, right? More salts on the opposite side. ECF would say that ICF तेरी चाय ज़्यादा मीठी है, right? Let me send some water so that अपने दोनों की चाय same हो जाए. So it would do what? There would be transfer of water from ECF to ICF. Correct? ECF to ICF. You are right. So there would be increase in the volume of ICF. Perfect. Very good. Right? And now, bichara ICF, who just can't do anything, his chai will be, because only the water has come. Sugar to jitni thi utni hi hai. Right? More water has come. So osmolarity of ICF would decrease. No, same. How can it be same, yaar? Why same, Jaydev? Same kaise? You got it? Right? You have chai thi, right? Normal chai, uske andar you have added thoda extra pani. So yes, it will become fiki. It will be dropped. Osmolarity would be dropped, right? And that is what really about this entire system, right? So these are the 6 things which will be working. Yes, that's right. It will be decreased, right? Just for the sake of one more new word, right? The figure which we were drawing over here, right? That is what is called as the Darrow, right? This is just, you should know the name, right? Darrow Yane, or the Yanet, it is called as Yane, right? Darrow Yane diagram, right? So that's the name of it. But you got the whole idea, right? So this is how you just go across, right? Correct check. Yeah. I told you that I find it too difficult to cram anything. So that's why I always figure out that बस ऐसी किसी मेथड से याद रह जाए, right? So that's it for today. And do one thing. Say when for the revision, right? What you do is you just write down like 1, 2, 3, 4. These are the conditions, right? And then every time this ECF, ICF, right? Over here you write volume, and here you write osmolarity, correct? And then add iso, hypo, hyper, ठीक? And then over here remove, right? That is loss, right? So this is like loss of iso, loss of hypo, and loss of hyper, and fill up, right? Every time fill up this ECF, ICF, ECF, ICF, ECF, ICF. Make such table, and whenever you are free, right? Because immediately if you'll do so, you'll be able to answer, right? Let some time really go, pass by, right? 2 घंटे, 4 घंटे, 6 घंटे, and then prepare this, keep this thing ready, right? Keep this table ready, and then ke chalo, right? Let's finish this, and you try to complete this, right? You do this thing 2 3 times, and as usual I always say, before you go to sleep, do this thing once, right? Then go to sleep. As you wake up, do this thing, and see, you don't have to worry for rest of your life. It will become part and parcel of your personality. You'll always be able to remember this thing crisply, right? I saved this file, and I'll put it into our folder, right? So just after a few minutes you'll be able to download it. Okay, it was really a pleasure talking to you. Thank you so much. Right. So see you tomorrow. Tomorrow will be a free day, right? So just let me know. Every day while having tea. Yeah, that is a very good idea. Every day while having a tea. Yeah, nice one. So just let me know whatever the questions which you. Yes, go ahead. Yes, you have some question. Uh, what Aishwarya asked. Sorry. Can we take diabetes mellitus in loss of hypertonic solution? I mean, what diabetes mellitus is a Kuller's concept, yeah. Aishwarya, I'm not getting your question. Can we take diabetes mellitus? Because diabetes mellitus is a condition, right? Is a condition. Anyway, right? These are the topics which will be taken in detail, right? Because these are some fantastic topics: diabetes mellitus, insipidus, all of them. Okay, mail me, right? I'll answer. So thank you so much, and see you tomorrow. And do send a mail for what we really want to discuss tomorrow, because it is like an open session, right? So thank you, and bye bye.